Yeah, thanks for the introduction. Yeah, so indeed, some years ago when I was working with Michael in Munich, I started Tenorth. Didn't expect it to live that long actually, and that people are still working with like the next generation of this, and it's nice to see that ideas are being developed further and that people pick up on that. So after my some years as a postdoc, I decided at some point, like three and a half years ago, to leave the academic world. I went into a startup in Munich called Magazzino. What we're doing is building mobile pick-and-place robots for warehouses. And in this talk today is a bit of a mixture of like a report from the field style. It's a bit of lessons learned on this way from doing academic research in these areas and actually bringing them into real life operation, and things that in hindsight often look obvious, but at this situation were not that much. And also some looks behind the facade of how these robots are actually programmed and which techniques we use, and also some of the techniques that we are talking about during this fall school are in some derived form also part of these robots and actually useful in there. So I'd like to start with a video of what these robots actually do. So we built mobile platforms. These they navigate autonomously through warehouses, pick items from the shelves and bring items into the shelves. So we focus on something particularly boring and simple, namely cuboid items, in order to make this problem not super complex. One sweet spot is shoes, because there's a huge e-commerce market behind that. Shoe boxes at first glance often look the same. The warehouses look very similar. And that's simplifying this in the beginning extremely difficult problem of mobile manipulation in the wild. What you may have seen, we built some specialized gripper. We built all the hardware ourselves because we found that with standard off-the-shelf hardware and just putting something together by using like a mobile platform, putting an arm on top and so on, you couldn't really solve the customer problem to a large enough extent. So you would leave the spots in the very bottom and the very top to the human, and those are the ones that are least ergonomic, and that's normally not what humans and the workers' union like to do. So if you want to get into a customer's warehouse and really want to have a business case, you need to do the whole thing, and that means normally you need to build your own hardware in order to solve this problem in a good enough way. So one very important lesson we've learned is when you want to go this path, found a startup, it's important that you have a vision that on the one hand guides you through your work there, but also excites you, and when you are excited about that, you can also convince other people. You can convince your future employees to work for you and follow you on this path, despite having lots of work and little payment and many difficult things to be solved. You have to convince your investors of this idea. You have to convince your customers to buy a product that is not yet a product and is in its infancy and doesn't really work yet. And it's really important if you have this longer term vision of where you actually want to go, so that also in difficult times you can stick to it. So before convincing your investors, you're normally running out of money, you don't know how to continue, you don't know how to solve all the technical problems, and then it's at least good to have a dream that sometimes motivates you. What's our vision? We observed that the robotics is moving away from the traditional industrial robots, or that's moving beyond that in a way. So there's still a huge application, of course, for all the robots that work in factories, that do the same thing over and over again and do this in a very good way. But there are many other areas where that doesn't scale, and these other areas require the robots to see how the world is different. So if they operate in open environments together with humans, for example, you can't just do the same task over and the same movements over and over again, but often your assumptions, your belief about the world is wrong. In the first place, you have to detect that and have to see what is actually different in the real world than what you believe the world to be. And based on what you're seeing, you want to adapt your behavior at runtime. So you don't just want to follow the same movements, but you really have to take decisions at the very small level of like where exactly to grasp something, but also at the larger level if you have to make a detour, if you have to do another action in between, if you need some recovery actions and so on. So it gets much more complicated if you can get interrupted and you have uncertainty there. You want to integrate that with lots of learning, because if you have to manually tune the robots to work in a new environment, that works if you have like one lab experiment, but it doesn't really work if you have dozens of customers and dozens of robots that are somewhere. So the goal is, of course, that the robots adapt themselves to changes that happen over time, but also if you throw them into a new environment, that you can make this efficient, that they learn what is different in this new environment from what they and their peers have learned before, and that you can get this. And of course, what makes things maybe a bit easier is that nowadays we have cloud technology, we have many things that don't exist in classical automation, and if you can base your system on modern accomplishments in computer science, everything that has happened in the last 40 years that is not really reflected in classical robot programming languages, that can make many things much easier. And our observation was, while we see this shift and these additional requirements, and while you have very good engineering support for these kinds, you don't have any support for this one here. So there's no guidance, there's no best practices, there's no software stack, there's nothing that you could actually get and use and buy if you wanted to build something at an application level for perception-guided robots that do things in the real world. So you basically have to start from scratch, and as you're going to see later, you need a huge team for that, and that's very difficult to build up and to maintain. So our long-term vision is that we'd like to build a software stack, an engineering toolkit that helps people to build applications for perception-guided robots. And we believe that it's the best way of doing so, or learning basically how to do this, is to do it yourself. That you need an application where you actually go all this way from the idea to actually going out into the wild, experience all these problems at the robotics side, at the behavior and data side, but also at the engineering and operations side, what it means to bring these robots out into the field and how you manage a large fleet of robots, how you ensure software quality for a system, how you optimize performance on a system that decides by itself. Those are all pretty difficult things, and that you don't conceive up front at the table, but that you really have to learn in the field. So our long-term goal is to, we call it ACROS, the Advanced Cooperative Robot Operating System, is to build the software stack that is designed in a way that AI is core of that. That while AI doesn't just mean deep learning, I think it's common here that also includes planning and execution. It includes lots of reasoning and knowledge representation. It includes many parts, but overall you can say that this architecture is pretty data-centric that we're doing. We'd like to generalize it to different robots in different environments, which is also crucial for having our own robots and customers there. We want to have it very modular so that you can use single parts without having to use the full stack. If you use the full stack, you benefit from it, but you don't have to. And what is a difference to many other toolkits that are there for easily programming robots, you need to be able to support a certain level of complexity in applications. So it's not enough in a Lego Mindstorms way to just chain like a sequence of things that works for the first demonstrator. But in order to be really robust, you need a complexity that sophisticated failure handling and many things are in there, and that your components help you to manage this complexity. Another thing we learned is that it's really helpful to start off your business with a problem that you're working on and not come with a completed solution, like some university spin-offs do that have like a finished robot that is the outcome of some project, and then try to find a problem that is solved by this. That is often doomed to fail because it's very hard to find something, or you try to bend your problem in a way that you build your narrative of why your robot is perfect for this. But it's really important that there's an actual problem there, because in the end any company has the purpose of serving some customer need, because otherwise nobody would buy these things, and it's important not to make it up. So for starting with building our system, we looked at different industries, and we found that intralogistics, warehouse logistics is something that is at the moment totally under-automated, and it's under-automated because the complexity, if you move from this highly tuned, very well-engineered manufacturing line that is built in a way that all uncertainty is eliminated, if you move just next door to the warehouse, you see that only humans are working there because the uncertainty and the variation is too large. At the same time, a warehouse is much more structured than some other environments, and it's still feasible to get into this. So what exactly are we doing? So if you look at the two main ways of how warehouses are operated, there's the man-to-goods solution, which means like people are walking through the warehouse and picking things up. And there's the goods-to-man solution, which means somebody is bringing the goods to the people are standing here and are picking somewhere. So here you need some automation, either like for Kiva or Amazon, like transporting the whole shelves, or it's like a shuttle system that is bringing some crates or some boxes or pallets or something to the front, and then the human is picking and is doing that. The problem with both is that they're really dependent on staff, and that it's very difficult nowadays to find people who are willing and capable of doing this job. So the society is getting older, the business is growing, often in e-commerce with like 25 to 30% per year, and so it's getting worse and worse, and people really have a problem, the companies really have a problem to find people to do this. At the same time, the labor costs rise of like 10 to 15% per year in these jobs. So the problem is getting more severe with any year that you have. And with all these automation solutions there, the problem is you really have a very rigid environment. So you build like an automated shelving system or something that has a fixed capacity, it has long lead times. You need like 1 or 2 years for building this. And if you're growing with like 25 to 30% per year and project that 2 years into the future, it's very hard to predict how much you're actually going to need, and probably it's too small when it's finished. And that's why we thought bringing mobile robots into this could be a pretty good application, because we go into existing environments. We work like humans do in these long rows of steel shelves. They're very easy to scale. You just add some more shelves. If you need more static capacity, if you need more throughput, you add more robots that drive there. And it's also pretty easy for the customers to start there. So overall, we chose it because on the one hand it's simple. You have structured environments. You can choose which objects you use. We chose the most simple ones of more or less cuboid items. And compared to many things that Michael talked about, you have pretty well-defined tasks. So you don't have to infer like where to get all the tools from, how to use the tools and so on. It's mostly bringing something from A to B, and somebody else tells you what to do. So the warehouse management system specifies these tasks in sufficient detail. At the same time, it's complex enough so that it can't be automated with legacy technology. So there is a need for automation there. And what's good for a startup, it's scalable. So you can start with simple objects, with small environments, with a single robot, with only one part of the task and few customers, and then you can scale. So you can scale at one customer and add more robots. You can add different kinds of robots for different objects, and so on. So starting small, solving a problem in some initial setting, and then becoming better over time and scaling is very helpful if you want to get into this business. And that also is another learning related to the objects. Keep things simple. So finding a niche where you see that you can become good enough for really solving the problem until the end. And the learning is that complexity will increase to an overwhelming degree on the way, even if you start with something that in the beginning you think is trivial or sounds trivial. So cuboid objects are not as cuboid. Stacks are not as stacky as they're supposed to be. You have lots of variation in these things, and having robots that really reliably work for extended periods of time with a high performance becomes complex enough. So we started off with a Toru. It's a robot that you've seen in the video. It's for like shoebox-like objects. We are currently developing Soto that can handle large cardboard boxes. So it's like the big brother of Toru, and also small load carriers that are like these more or less standardized plastic boxes that are often used in production supply. And the end game, if it's coming 2019 or at some later point, is still to be decided, will be a robot that can pick different kinds of items. But again here, we will choose some niche, some kinds of objects where you can specialize upon, and that is generic enough to cover a certain range of customers. So if you start off by doing everything, then it's very easy that you in the end don't do anything good enough, but you do many things up to like 20, 50, maybe 80%, but that's not really sufficient for selling these kinds of robots. So finding a niche where you basically, with the same technology, the same hardware, the same software, the same procedures, you can actually cover a broad range of use cases is really essential if you want to get anything done here. So once you've found that, the question is, how do you get started? Because in many cases, in the beginning, you don't really know which problem you're solving and which problems are going to find you on the way, and that will surprise you when you get out into the wild. We adopted a fast iteration approach that is pretty common in software startups, and it's a bit harder to do in hardware startups, because on the one hand, hardware iterations cost money. If you build a software iteration and it's pretty crappy, then you can just throw it away and do the next one and do a new release, but it doesn't cost you anything apart from a bit of computation time. If you build a robot, you have to pay for it, and afterwards it's scrap metal. And on the other hand, it also costs you time. So you have ordering times, you have assembly times, and until you have the next hardware generation, it's easy to lose a few months there. Still, we think it's very helpful to go there. What we did in the beginning, and what we closed our first financing round with, was this concept drawing. So it was only a rendering. It's a robot that in this animated video could also extend here. A telescope had this little arm with a little suction cup in there, and the idea was to use this thing to move through the warehouse and pick items. It was enough to convince some first investors, but it was of course nothing that could have worked actually this way. What we did afterwards was to just buy some mobile platform. We had our self-constructed gripper for books and put 2 vertical axes on top of that. It looks pretty crappy, but we dropped it into a real warehouse very soon. We built this in a matter of a few weeks, and that gave us a base for starting the software development and starting to learn how the world actually is there. What we also learned is that if you just put a case around the same thing, it looks much more professional, and so it's actually the same thing inside. And with this one, we already went to a customer. It was a customer shipping books at that time, and did the first picking test there. And that gave us insights about how you have to navigate from where to where you have to pick, what your height is actually, that it doesn't make sense to drive back and forth for every object on its own, so you needed some storage there. It also showed us that there were some low parts of the ceiling, so you needed some telescopic part to get underneath them, but also to get high up and so on. And that we also needed to reach the lowest level, which all we couldn't do with this one. And then the first design was this Toro that had this rotating tower, the telescopic one, and had a backpack in the back so that you could store the items and have longer runs through the warehouse where you're collecting many things and then drop them off at once. We noticed that the book market where we started in is actually not that attractive anymore, so it's on the decline. There are not that many players, and also they store books in different ways. Some are standing, some are lying. So we moved towards shoeboxes. Shoeboxes have the challenge that you have loads of different ones, so different models plus all the different sizes. So normally you don't find stacks where the same ones are on top of each other. So you need to pull the bottom ones out of the stack if you want to fulfill an order. The result was that we had to construct a new gripper. It's a suction unit in here and some kind of pushback on the top, so we can pull out the stack and push back the upper objects of this, and thereby also, if you have mixed items, get the lower ones out of these. Some of the requirements that you only notice when you're actually there in the field. And now the recent generation of this looks a bit sleeker, but has been totally redesigned. That you have higher reach, lower manufacturing costs, all the access are faster, the price is lower, the assembly and service has been optimized. So in the first version, our designer convinced everybody that there shouldn't be any screws visible from the outside, which looked very nice, but it was an awful thing if you wanted to, if you had to service anything. So it took like 2 hours to disassemble some parts of the case out there. And afterwards we convinced him that it's an industrial product and that it makes sense maybe to relax some of the design constraints there. So if you really want to manufacture them or outsource manufacturing, thinking about how to build them together is really important. And then at some fairs, people approached us and asked us, okay, it's a nice thing, but can't you do it in larger? So we came up with the concept of Soto. Soto also has the backpack, but instead of having the tower, it has looks a bit like a forklift with a gripper on the front. Also here, once we had the very first prototype, we brought that to the customer to get experience of how the world there looks like from the robot's point of view, which situations we're facing there. And the next product that is more on the horizon is then using the same platform for picking plastic boxes in production, where the challenge is less grasping these different items, but more from where to where you have to grasp them. So there are these gravity shelves where things are put on the top. This is a worker in the assembly line that takes these things. And also here, normally the supply is completely manual, because for automation it's too difficult to put it in up here. To pull it out here, there's of course some stopper over there, so you have to lift it, pull it out, detect where things are and so on. It's something that couldn't really be automated beforehand, but if you have a robot that is mobile and can perceive the world, that's something that can be automated. So for keeping things together on this way, we've found it's very important that you have a very clear architecture that is of course simplifying things, that is like putting things in a more polished way, but that should convey like the main ideas of how we assemble the system. Because otherwise, if you're growing the team, if you're getting to different problems and so on, it's very easy to lose that focus in your daily business, and to have some system that is just built up from very many components and doesn't really follow the guidelines that you're having. So this is how our architecture looks like. So we have different levels of code that are on these slices here. The lowest one is some hardware abstraction like ROS drivers and so on, not very interesting. Then we have the different robotic algorithms like for localization, for path planning, for object recognition, motion planning and so on. They are tied together at the third level that is still running on the robot by our high-level executive that I'll talk a bit more later. So it's similar to Kram here in the group in Bremen. And that is basically defining the application level. In which sequence do you do what? How do you handle which kinds of problems? And basically defining all the high-level application flow. All the robots are integrated into some local cloud at the customer that is assigning the tasks to the different robots, coordinating them, but also deals with information sharing between the robots. And all the robots are also connected to our global cloud here. And what I think is essential about this architecture is not only to have these layers of code that's pretty standard, but at the core of it have representations, have descriptions of different things. So the knowledge representation here is really an essential part of this architecture, and especially important is that it's shared between the very low levels and the cloud level. So every level is describing the world using the same terms. And if you're seeing something here, you can pass it up here, you can process it, and then pass it down here, and both sides understand each other. And in essence, we have a description of the environment, we have a description of the objects that we are manipulating, we have a description of the robot itself. So it's not only the hardware model, the URDF, but also all the electronics parts, capabilities, calibration parameters, many things that describe this piece of hardware or this type of hardware. You can also generalize there. And also the tasks we're performing are essentially a description. So our behavior tree is not a program, but it's a data structure that describes this and presents the rules. And since all of this is data, it can be aggregated, it can be learned, it can be processed, and you're much more flexible with this than with just having a normal coded program that you can just execute. So it's not as elegant as it would be in Lisp, of course, where you have this complete duality between code and data, but I think it's as close as you can get while avoiding some programming languages. so I already mentioned this third layer, the behavior coordination, and so during my time in research, I worked, of course, with all the tool set also used in Michael's group, developed some parts of that. But when going into this endeavor of starting a startup, I didn't really want to be biased. So I found pretty cool how it's all working, and had good evidence of that in research applications, but I wasn't really sure if that is actually the most important thing when you want to build a system in the real world. And so we went there and basically checked what are the problems that we have to solve and what is the best solution for them. Is it sometimes maybe better to just code something yourself, or is it better to have like a clean or model-based system? And in many cases, actually, it turned out that the model-based or this descriptive solutions do have their advantages, and will only allow you to manage the complexity that all the system has, so that it's you can then understand how the system is built. You can introspect that and debug it, and many things that would be much harder if you would just program it in some way. So when we started, we looked at basically this scope of different ways of how you can program something. This is of course massively simplified. We didn't put it into one dimension, but for the sake of simplicity here. So of course on one hand you have like PLC controllers, the classical robot programming languages. Many people use state machines for programming the robot behavior. On the other hand of the spectrum, where you can manage lots of complexity but also have a pretty steep learning curve, is probably CRAM. Somewhere in between is AI planning, which is can be tuned to a very high complexity, can be very simple to some extent. But it's mostly covers like the planning side and not so much the execution side of things. We chose something in between, and we found that behavior trees are a pretty nice representation that combines many of the benefits we were looking for there. Behavior trees were actually conceived for complex computer games. And especially for controlling the non-player characters there. So I'm not a gamer, but I learned that there are like some people, some personas that are controlled by the humans, but there are some others that are controlled by the robots. And if you have, for example, a smith or a fighter or somebody, these people have a pretty complex activities that they're doing in some simulated world. They have to be pretty reactive. So when they're being approached, they have to start a conversation or have to start a fight or do something. When the fight is over, they normally get back to normal business. They have to do this in a pretty realistic way, and they have to really do it fast. And what we also found attractive is that in these cases, it's not the hardcore programmer that is programming these things, but it's the domain expert, is the one who's designing the conversation, who's designing the model, but he doesn't have to be like the super specialist in programming. He doesn't have to think about like massive multi-thread programming, data sharing and so on, but it's somebody who describes basically what the outcome should be, and not so much how it's done in the background. And that's also what we'd like to have with this one, that people can focus on the application level, on designing what the robot should do, and not so much on how it's implemented in the background. So for explaining, we use this simple use case and built a behavior tree for this Pac-Man thing. How does a behavior tree look like? First, it has a graphical representation. We have a browser-based editor, but in the background it's of course a program that is running and executing this tree. The nodes in the tree have either here these leaf nodes. They are either actions of doing something in the world, or they are conditions of checking if the world is in some state. In between, they are connected by so-called composite nodes. And each of these nodes, it's pinged in a repetitive way, so normally at something between 5 and 100 hertz. And whenever it's pinged, it returns some return state, which can either be success or failure or running. So if it's success, it means it was successful. Failure is also obvious, and for running, it means it has started some action, but the action takes longer time. But in order to pass on the control to something else, we are basically returning this, and the next time we are pinged, we are maybe finished, or maybe we still need some more time or so. But since we're not stuck in this node, but returning control to the higher levels, we can have this reactive fashion that we're having in here. And these composite nodes basically take the return value of the children and decide what to do next. So this one here with this question mark is a selector, and the semantics of this one is it asks the first child. If the first child succeeds, it's happy and succeeds as well. If the first child fails, it asks the second one. If all children fail, it fails as well. So basically it's trying them in order until one of them succeeds, and then it also returns success. This line here is a sequence, so it asks the first child. If the first child succeeds, it continues with the second one. If the first child fails, it also fails and passes the result up there. And with these two very simple composites alone, you can already build a pretty complex program, and actually behavior trees are fairly similar to imperative programming languages. So you have implicit loops by having the iterative execution, you have sequences, you have conditions, and so on. So many of the structures that you have in classical programming are also in here, so you're not really limited in what you're doing. And in between you have these rhombus-shaped things that are composites with a single child, and they just manipulate the return value of their children. So for example, this inverter here, if the child returns success, it's going to return failure. If the child is returning failure, it's going to return success. And that allows you to use the same check, for example, multiple times without having to reprogram this one. You can use it for the check and the opposite check. You can also have a loop, for example, so if the child says, I'm finished, and then you're just not passing the finished up, but say like, okay, do it again, do it again, do it again. Then basically everything is happening in here, and to the upper side is just returning, I'm running, I still need more time. And to the lower side, it's just creating this loop structure. And yeah, basically covering all of this. So if we go into this Pac-Man thing here, so we're implementing some simple reactive pill eating behavior. You're first going in here, you have the selector, it's asking the first child. You have the sequence, it's also asking the first child, is the ghost close? Assuming there is a ghost, this succeeds. Sequence switches to the next one, it's again a selector. It's asking here the sequence, is the ghost scared? Assume it isn't. Then this one fails as well. This one fails, it's trying the second one. It's going in here, the sequence asks the first one. Is the ghost not scared? Is the ghost scared? It's inverted, it's not. And in this case, it's avoiding the ghost.
So you're asking in the first place if there's a ghost close, and if not, then you're asking if the ghost is not close. Is that right? So
yes.
Okay.
So they are like the complementary checks in this way.
We're not assuming that this is a Boolean value, like finding them.
We are assuming that it can change over time. So it could, in theory, also change in between here. I mean, if you have something that doesn't change that fast, or that is like totally observable, then you can also just get rid of that, and so on. And so what's nice about here is if here in this avoid ghost is being triggered, it returns running, it goes up here, and then the next sequence starts. And now it's basically re-evaluating these different steps, and is re-evaluating if avoid ghost is actually the best thing to do at the moment. So it could be that the ghost got scared, and that you should actually switch to this chase ghost thing. Or it could be that by avoiding, you actually got far enough away from this, so it's not close anymore, and then you should actually eat some pills and have a happy life over there. So the nice thing here is that you're really constantly re-evaluating what you're doing, and in effect, the control is pretty much jumping here in the tree. So it could be that you're somewhere down in here. At some point, something more important comes up, so everything is more to the upper left, is a higher priority. Then you're doing something here, but afterwards you're also then jumping back into what you've been doing originally. And that's a pattern that you also like to have in robotics, that you have like some normal operation. You need to handle some other cases, but once these are handled, then you want to go back to what you've been doing beforehand and continue your original task. And another nice thing, mostly from an engineering perspective, is all of these tasks only have a single parent. I mean, it's obvious for a tree, but if you look at a subtask, you can use them as a module, and you can put that in and just have a single connection that you need to do in order to integrate it into this execution flow. So if you think about state machines, then each and every node has to know where to jump. So you execute a node in a state machine, you say, like, under this condition I'm jumping there, under that condition I'm jumping there. If you want to have highly reactive behavior, then you basically can jump from everywhere to the failure handling routines and back to your original things, which means that you're pretty quickly ending up with a very highly connected structure there in the state machine. That's really a nightmare for refactoring. In this case, you can really condense things in a very modular fashion, just insert them at some places, and can also build up a library of these subtrees. So, just checking that. If you want to use them for robotics use cases, it's easy to extend them, and we also, getting inspiration from Crum and others, added some more nodes instead of just the sequence and the selector that encoded some robotics design patterns that are pretty common. So one is, for example, the memory nodes that don't always start re-evaluating something, but if you're in a pick and place sequence, for example, and have already picked the item, then you want to continue from there in the next traversal of the tree. You can have parallel execution and succeed if one or all of the children succeed or one or all of them fail. So it's a bit trying different alternatives or doing many things in parallel. Retrying something common, and especially this recovery composite proved very helpful for us. The semantics is there. You have a main task that you're doing. If this main task fails, you have n recovery tasks that you're trying in order. If any of them succeeds, then you're continuing with your main task. And that's a pattern that you have in many cases, that basically you have different ways of fixing a problem, and you don't always want to program these control structures yourself, but in this case you just have this one node that is encoding the semantics, and you have the same execution all the time. What we also added is a kind of scoped variable handling. So the original behavior tree only looks at the control flow but doesn't consider data. And many people use like blackboards, which is in fact some global variables that you have in the tree. And if you have different people who edit the same tree, then it's very likely that they use the same name. Target pose is something that we had several times for navigation and grasping and so on. And then you get weird behavior if the robot tries to navigate to some place inside the shelf that somebody else set as a grasping target pose. So in our case, every subtree actually spans its variable scope. And in effect, the behavior tree actually gets very close to like the normal programming language, where you have like every subtree as a function. You have the input keys as the arguments to this function. You have the normal control structures that are in there and can actually program in a way very similar to what you've been doing in a normal text-based programming language, but in the web in some pretty easy editor, where you can define also like everything that you can do in Python argparse is also there for the different arguments that you can pass in, and then do introspection at runtime, step through that, have a debugger at behavior level basically, where you can step through the different things and so on. And this structure really helped us to define the behavior of this robot. Our behavior tree has like some 500 nodes, and you're running them into a pretty in very reactive fashion. So the behavior is really jumping between different things that it's checking, constantly monitoring some things, then interrupting the normal execution flow, doing some recovery actions, doing some other things. And for keeping track of that and debugging this behavior, it's really helpful to have some clear model behind that, where you have some defined semantics, where you can have local scoping and local testing of some subtrees, because you have a defined interface and you have clearly defined semantics of what these things are actually supposed to do. And get some of this uncertainty out of this, because if you really wanted to program this all yourself, that would be quite a bit of effort in there. And another thing, we also noticed that the power of reasoning is very helpful also in many of these applications. We have a database that represents our environment, our objects, our tasks, many things. On top of that, we already have a logical inference layer that allows us, for example, to do spatial inference on the warehouse, so that we can encode rules of like the highest compartments in a shelf, the compartments at the end of a shelf that sometimes have to be handled in a different way, neighboring compartments and many things. So they're very simple reasoning tasks actually. But it helps if you don't have to program them every time yourself, but you just have a layer that you can ask and that computes them for you. Another use case is capability reasoning. So if you have a hardware error in your, for example, one of the motors in the gripper has some overcurrent or dies or something else, the question is what to do or what can you still do? And the gripper motor should of course disable all kinds of gripping motions until it's recovered, but it shouldn't stop the robot from navigating back to the charger instead of dying somewhere in the warehouse. So really reasoning about these capabilities and the capabilities that get lost by certain problems that you have are essential for having robust operation there. And also related to that, some diagnostic reasoning. If you see observed problems, you want to decide what to do, and if you have to report the problem to the service personnel or to the customer, you also want to explain what the problem is and what's probably the best way of solving this problem. And that's something where we use some diagnostic reasoning on top of these data structures in the database in order to come up with explanations and with recommendations of what is basically a good step to do there. So it's a pretty ugly drawing, but it shows this concept. So in this behavior tree, you have the different nodes, and you have different ways of how something can fail. Of course, it can be that you're trying some action and it just doesn't succeed. You want to navigate somewhere and you can't, or you're checking something and it doesn't work. And that's covered by the normal structure of the behavior tree by returning failure, 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 and then this branch fails. That's like the normal thing. But in addition to that, you can have some other kinds of problems that are, for example, caused by the robot state. Some motors going offline, some sensors stops publishing data, localization diverged, and many things that just happen. And those are, in our case, monitored by using ROS diagnostics. And there we have some explicit robot state model that also includes the different capabilities the robot has. And then the reasoning engine can, of course, on the one hand, be asked by the behavior tree. So it's evaluating this robot state and is answering basically what is still possible and what isn't. It can also be used by we call it Toro Control Center, the one that is allocating tasks, that is checking basically what can this robot still do, which tasks can I still assign to that guy, but also by the graphical interface that we provide to the customer in order to understand what is still possible there and not. If you want to bring these robots into the fields, you notice that the first things go easy when you can define your test cases. If the customers start giving you the orders, giving you the objects and everything, and start expecting long-term failure-free operation and performance and so on, then things get difficult. And if you then have built this very complex system with like 100, 150 ROS nodes, 500 tasks in the behavior tree where the behavior is jumping around, understanding what this robot is actually doing, why it's doing that and why it's so slow in doing that. If it's like an algorithm that is too slow, if it's an algorithm that fails too often and you have to retry, or once we had the problem that winter season started, the shoes became larger, which means we had less mechanical tolerance in the gripper, which means we had to navigate in a more accurate fashion, and otherwise the robot pulled the box in and it collided with the gripper. So we had like grasping errors that shot up in this time, or slower pick performance because of more grasping errors, because of more retries, and figuring out that this is actually the problem when you're not sitting next to the robot, but the robot is somewhere else in this warehouse, really requires lots of data handling. And there it's super helpful to have a system that you can introspect, where you can log which behavior tree phases are executed, which are the parameters for that, how long they took, what was like success, failure arguments, and so on. And we now have 2 people who just work on data science on top of the logged operation in order to provide statistics of what the robots are doing, which components are going well, and we use that for steering the development onto those aspects that have the highest impact on robot robustness and performance. And those are things that are actually also shown to the customer. So they get live reports of the availability, the picks per hour. Here, for example, during the day, what was the robot doing all time? So here it was green operating, in blue it was waiting for orders, in red it had some failure times and so on. So for really understanding what are the patterns and not seeing just the aggregated numbers, but really diving deep into the problems. What we also learned is super useful is contributing and participating in open source communities. So we use ROS as the basis. We also have 2 ROS.com maintainers in the team, 1 PCL maintainer, different other people who are really contributing to core parts of this, partly in their free time, but partly also as part of their job at Magazzino. It helps us to just try some code. We don't have that much of the normal ROS code in the system, but some parts, especially the tools like Arvis, are super helpful. It's very helpful for us to get in touch with candidates and also to give back to the community. So if you want to find people who are able to work in this system and if you want to onboard them quickly, it's really helpful if you can put, basically piggyback these standard procedures that ROS provides. So people get productive after a few days. If they know ROS, they know how to navigate a ROS system, even if they have never seen our system here. And that really helps us to scale the team. How do we relate to the other parts? So ROS provides, like, they call it like the plumbing connection between nodes and so on. The tools like Arvis, there are some capabilities like the navigation stack or so, and this ecosystem of developers that is in there. And then you have initiatives like ROS Industrial that add things like hardware drivers, planning libraries, some tools and so on top of that. But what we think is still missing is something more at the high level parts. So how do you ensure quality at the application level? How do you do robot in the loop testing for all your software? The behavior control, like remote debugging tools. We have, for example, an Arvis that works over the internet. So you can open it in the evening on the sofa and basically visualize all the robots into one customer site all together in one 3D thing and debug behavior flows in this way. That's super helpful if you want to scale this here. And also all the way of how to log and manage information, how to do learning on this. Those are all aspects that are not really covered in ROS that we had to add, but that we think are also useful if you want to build another kind of system on top of ROS and actually deploy that in the real world. And yeah, so we're also starting to give back. It's pretty old slide, but whenever we see that something is not essential to our business, like a camera driver or also our navigation system, it's something that we're also open sourcing, and that is not only a giving away, but also getting things back. So for example, for move-based flex, like an improved version of the navigation stack, we also got lots of pull requests. People are actively developing that and helping to improve the thing that you released in the beginning, and it's not a one-way thing of just giving it to somebody else. And one last thing, when you starting small and growing the team over time, it's also important to think of growing the people. It's normally something you learn in hindsight, but giving people the opportunities to grow and learn and also to develop, for example, into a team lead position is really essential if the team gets larger and larger. So Magazzino was founded in 2014 by 3 founders. When I joined in 2015, we were like 8-10 people back then. Now we are 103 people, 50 of them in software, and you have to develop many structures on this way. So in the beginning, hiring is cool and nice, and everybody has a single goal to focus on. When you have different robots, different customers, a large team of 50 people, then you really have to think about how to manage this team, how to make sure that everybody is on the same page of what is the top priority, how you distribute the tasks, how you also keep people involved and happy and give them the chance to grow there and not just go somewhere else to other companies that are hunting for people in Munich. So there are lots of challenges on this side as well. So it's not only like the technical side of taming this robotic beast, but also really about building the organization in the background and transforming this organization from being very fast for hacking a prototype in the beginning into being quality-driven, structured, operating things instead of building things, and that requires pretty different structures, different skills, different people in the team also to some extent. And yeah, and what's also good and sometimes challenging if you have a very young team. So I'm 36. I'm one of the oldest one actually in there. It gives it's lots of energy in the team, but also sometimes maybe a lack of experience that is in there. So thinking about how senior the people should be, what is good experience when to bring in older experience is something that you learn afterwards, is also something important to think of. So to summarize, we started off with this idea of building in marketing speech, the brain or the control stack for perception-guided robots. We're doing that in mobile pick-and-place applications for warehouses, for warehouse logistics. We think that it's a very good use case because it's simple enough that you can actually get something done in a good enough way, but it's also complex enough that few other people are crazy enough to tackle that. And yeah, so I think it's a pretty exciting thing. So we've about 20 robots in the field, and we sold about 50 robots at the moment. And of course we're hiring. I know you're all happy in your PhD jobs, but if you know somebody who is willing to work on robots in Munich, please come talk to me. Thank you.
Yes, thanks for this talk. Any questions?
How do you handle security with ROS? Do you lock everything down in a sandbox? Or?
Yeah, it's one of those topics that people often claim as a disadvantage of ROS. I mean, it's very open, and once you're in the network, of course, it's you can connect to everything. We are restricting ROS to the network on the robot, and basically shutting off everything to the outside. So we have encrypted and authenticated connections in between. We have our own public key infrastructure for encrypting all the connections between the robots, the TCC, the external parts, and so on. And there you can just base everything upon normal internet technology. So firewalls, SSH, VPNs, and so on. And thereby use some proven techniques and not something that some PhD students built. So that's our approach for combining these two worlds. So it's, on the other hand, super helpful for us that it is a very open structure, because then you can put your test probes to everything, log everything that you have, and really have meaningful introspection.
I'm still kind of puzzled about behavior trees. So if a programming language designer, right, they would make up language which would look more like RAM, right? So they would have something like semaphores, they would have critical paths, so some control structures that you expect are really occurring, right? On the other hand, you have behavior trees which are very successful in game programming, which is quite complex, right? So I guess one of the questions is, do you have to realize some patterns in the behavior trees that correspond to the programming construct that they would have put in language in the first place? And also, I think the other question is, I mean, you're really going for software engineering, industrial strength products, and you're not going all the way that how programming language designers are going, right? So I would like to know kind of a bit of your view on these aspects.
Yeah, I mean, behavior trees do have some limitations compared to other programming languages, of course. And so if you have like parallel execution, and you want to have like semaphores or mutexes or other kinds of things, like synchronization between these different strands of execution, that's something that is not natively supported by behavior trees. You could put that in, for example, by having these decorators that are allowing access to some subtree only under certain conditions. So you could have like some counting semaphores of saying like only n instances of this may be active at the same time for restricting access to some shared resources, for example. You could have some coordination between different things by that as well. And there are good and bad things about that. No? I mean, the good thing is, of course, that you have some increased functionality. The bad thing is, on the one hand, that it breaks the design pattern of having independence of the different branches. So in the raw behavior tree, no branch knows of any other, so you can just take it and connect it, and basically it works out of the box as long as basically the input is there. It's very functional in this way, so you don't have any side effects. And that's, of course, broken if you connect it too heavily to other things. Another problem is that it adds complexity. So the people who program it have to be familiar with these concepts and have to be able to track them. And especially if you have lots of jumps in the execution, the proper release of the locks can be something very difficult. So at the moment we deliberately chose not to include it. It's somewhere in our design documents, but marked as unimplemented, because I wanted to wait until we really find a use case that we can't really solve with anything else. We are kind of shortcutting the whole parallel execution thing by using ROS actions in the background. So you don't really have multi-thread programming, but in a way it's like multi-process programming, where the processors can also live on different computers, because you have the ROS action interface in between. And basically for starting these different things, it's then sequentially calling the actions of the children while they are running and then collecting the results in the back. It's of course a massive simplification of things, but in our case that's also sometimes a good thing. So
if you would go to applications, say, I don't know, programming drones that do some application tasks where basically the requirement for concurrent control is much higher, could that change things, or is that...
Yes, definitely. I mean, it could also be that if you have like some subsystems that you want to control, and where you have like different people controlling the arm, for example, that are like different parts of your tree controlling the arm, and you want to restrict that just to one at a time, that could be something where it's then always the part, do you do this coordination at a lower level, so pretty close to the hardware, or do you raise it up to the behavior tree level? I think it's definitely not the right thing for really having some real-time control parts. Also, if you look into formal verification, that's of course much easier if you have a state machine. And when you have there's more infrastructure for these kinds of things there. But for programming these reactive control programs, it proved pretty useful for us. And especially this modularity is something we're heavily exploiting, that we also, for example, have one navigation subtask. It's very similar to the plans and QAM. I think it's the same concept, that if you program something the right way once and then you use it at different places. And for navigating from A to B, we have to apply some safety constraints. We have different ways of how we can actually drive through the environment. But it's the same thing if we want to drive to the pickup location of something, to the put down location, if we want to drive to the charger, or if we just want to drive somewhere for having a look at some compartment. And those are actually all the same tree. And once you fix a bug or have some improvement at one place, then it's instantiated in all the other parts as well. And those very basic things that you of course know from any kind of like normal software library are super valuable if you also can use them in this high level behavior modeling.
Did you mention, in one of the slides you mentioned that you were having the GUI to communicate with the user. Does that mean the user at some point is programming new behaviors to the robot?
It depends on which user. So the warehouse worker not. So what we're trying to have is the same behavior tree we do have the same behavior tree for all customers and different customer processes. So sometimes, for example, the pickup location is specified as like a small compartment, so you know pretty exactly where it is. Sometimes it's like a whole, like a shelf on wheels and called a pick cart, where you have to search for items. Sometimes the target is specified. Sometimes you can choose a target completely freely and randomly in the whole base floor of a warehouse, for example. So there's some flexibility that is built into this, but we try to have the same. If you wanted to use the system for something completely different, so we use behavior tree, for example, also inside move-based flags. So inside the navigation stack, there's a second behavior tree execution that is controlling the navigation behavior. Which evasion methods do you use? How do you handle problems if some goal state is in collision, target is in collision, something else? What happens there? Then, of course, you're programming that, and you're doing this using this web-based editor that we're having there.
One last question.
Good one.
Yeah. If you got your robots driving around in these warehouses, are there still humans doing the same job? Or okay, so they are working together, or maybe?
Yes, and that's a blessing and a challenge. I mean, the nice thing is if you design your process in a good way, then if the robot can't pick something, then you can pass it on to the human. So you can live with not having 100% reliability, but if there are some cases, be it an object is too large, or it's like also in shoe wares, you have some scarves, some socks, some other things that the robot can't handle, then they can go to the human. On the other hand, you have to comply with safety regulations, so you need special ways of how to drive, and being fast and being safe at the same time is something very challenging to do. Yeah. And I think what even has more impact is that humans change the environment. So they move items to different places. You don't have control about these things anymore. We of course do share where different robots have put down things, so all the other robots have access to this information, how another robot left this compartment in a way. But it can always be that the human came in between, changed something, picked some items from that. So there's lots of uncertainty induced by humans into the environment. Yeah. And,
Thank you.
Thank you.